Join me in welcoming Roshan Shariff, our first student speaker. He's going to tell us about efficient planning in large MDPs with weak linear function approximation. All yours, Roshan.
Thanks, Abhishek. And yeah, thank you all for coming to this talk virtually, of course. So this is a follow up to the work that Shaba was describing in his talk last week. So I'm going to give more details about the work, and this is like a theory heavy talk, right? So there's not going to be a lot of experiments or anything like that, but I'll try to go slowly and give the intuition for what we're doing rather than the technical details. And if anyone does want more technical details, then we can use the time at the end to go further with that. So the title of the talk is Efficient Planning in Large MDPs with Weak Linear Function Approximation. Everyone should know what large MDPs are. Large MDPs are they have so many states that you can't do any computation that depends on the number of states. And weak linear function approximation, I'll talk a little bit about what that means, or in particular what weak means. Okay, so I'll first define the problem that we're trying to solve, and this is the MDP planning problem. So the problem is that you're given a particular state S, and you want to output a particular action A, right? By the way, I'm just going to assume that everyone here is familiar with MDPs, the idea of actions and states and so on. If anyone isn't, then feel free to speak up and I can give more details on anything. Okay, so yeah, so the MDP planning problem is you have one input state, you have to produce one random, possibly random action A. And of course, we want this to be a good action, right? So what does that mean? We want the value, so this action defines a policy, right? So one action at a time, you are producing a policy. And we want the value of that policy to be close to the optimal value of the MDP for every single state, right? So you can think about this as, I don't know where the MDP is going to start. So for every possible starting state, I want the value of my policy, the gamma discounted value, to be close to the optimal value for that start state, right? So this is a very strong condition, but like, this is basically the only reasonable thing that we should hope for at least this much, right? Since this is a planning problem, we will assume that whatever algorithm is producing this one action has access to a simulator of the MDP, right? It's just a one-step simulator. And I'll talk later about what that means. And for large MDPs, my requirement is that this computation to produce one single action cannot depend, the amount of computation needed cannot depend on the total number of states in MDP, right? So there should be nothing in my algorithm that depends on the number of states in the MDP. And in particular, I can't even call the simulator for every single state in the MDP, because that would itself be way too much. Okay, so now, obviously, in this generality, this problem is basically impossible to solve, right? You can show that there are various bounds that you basically have to look at every single state in the MDP to find an optimal action, even for one particular state, right? So that doesn't work. So we are going to make some assumptions, and we will show that under these assumptions, we can solve this problem, right? The first assumption is pretty common. It's linear function approximation. So the idea is that somebody has given you a feature representation, right? So it's a function that maps states to d-dimensional vectors in RD. And further, you happen to know that this is a good feature representation to represent the optimal value function, right? So there is some weight vector theta such that when you you compute the value function represented by these features in theta, then the difference between that and V star is small. We are not going to say it's 0, but we're going to say it's small. So that's epsilon, right? And of course, no matter which feature representation you pick, there's going to be some epsilon for it, right? It's just that epsilon can be really big. And we are going to say that epsilon is small. And in particular, what that means is that our planning algorithms performance can degrade as epsilon gets bigger, right? So we're not going to make any concrete assumptions on how big epsilon is, but I'm going to present an algorithm whose performance gets worse and worse as epsilon gets bigger and bigger, right? So I hope that makes sense. So this is just a measure of the quality of the function of the feature representation. We're just saying if somebody gives us a high quality feature representation, then I should be able to produce actions that are almost as good as if they were drawn from an optimal policy without any computation that depends on the total number of states. Okay, so hope that made sense. I'll move on. Okay, so now you might ask, is this assumption enough, right? Suppose somebody gives me a good feature representation and tells me that the optimal value function can be represented with that representation, not any other value function, just the optimal one. Is that enough to produce actions that are basically as good as if they were from the optimal policy? And this is a weird question, right? You might think the answer is yes. Like, if you can somehow approximate the optimal value function, you should be able to draw actions. But unfortunately, it turns out the answer is no, with some conditions, right? So there's an asterisk there. So there's this paper by Du, Kakade, Wang, and Yang from last year. And this says that even if the optimal value function can be represented quite well within a factor of epsilon with some feature representation, you still need to look at basically every state in the MDP to be able to find an approximate action, right? So this is saying that if you have an MDP which is episodic, undiscounted, and has horizon H, then you need to look at 2 to the H states in general to be able to find even a single action that is close to optimal, right? And if you want the resulting policy to have that same epsilon error, right? So we said that our feature representation had epsilon error, and if you want the resulting policy to also have something like epsilon error, then you basically need to look at 2 to the H states, which is exponential in the horizon. That's not good. Okay, but if you can relax your condition a little bit, then it turns out that the answer is yes, sort of. Again, there's a little bit of an asterisk there, so I'll talk about what that means. So now we are going to say that our goal is no longer to achieve an epsilon accuracy, right? So epsilon was the quality of the function approximation. But what if I can relax that a little bit, right? So instead of epsilon, I add in a factor of H squared. And H is 1 over 1 minus gamma, right? So H is the effective horizon of our planning problem because we are in a discounted setting now, right? So if your algorithm is allowed to not just achieve epsilon close suboptimality, but H squared epsilon, and there's a factor of square root D. D is the dimensionality of our feature representation, so that's not particularly important. Then there's these 2 papers that both say that in this situation, you can actually find an action by only accessing your simulator a small number of times, right? So you don't have to simulate every single state in the MDP to be able to produce an optimal action. But a problem with both of these works is that you still need to look at the features of all the states, right? So you're not simulating all of the states in the MDP, but you need to, it's like somebody gives you a feature representation and you need to figure out what the features are for every state in the MDP, basically, to be able to solve this problem. So even though the number of simulated accesses is small under this setting, the amount of computation is still really big, right? Like if your number of states is really big, even if you have some sort of feature representation like a neural network or something, you just do not have enough time to look at every single feature vector for every single state in the MDP. And so even though this is sort of a yes, in that you don't need too much simulation, you still need lots of computation, right? So that's not good enough for us either. Okay, so that brings us to our work, which is again a qualified yes, right? And in our work, our goal is to have a small number of simulations and a small amount of computation, right? So we don't want any simulations or any computation to depend on the total number of states. But instead, we will need to make one extra assumption, right? So somehow we will need to make an assumption that says that you somehow don't have to look at all of the features of all of the states to be able to do this, right? And so we will assume that there is a small set of core states. And in the next slide, I'll talk about what the assumption is exactly. And we will only look at the features of the core states. And we will only simulate the transitions from the core states, right? So as far as the algorithm that I'm going to describe later, as far as that algorithm is concerned, there are no other states except for the core states. And the computation will scale with the number of core states, the number of actions, the feature dimensions, and the horizon. And all of the scaling will be nice, right? So they will all be small. It'll scale in a nice way with all of these things. But in particular, nothing will scale with the number of states in MDP, right? Okay, so here's our assumption, and the assumption on core states, it's a geometric assumption, right? So we're assuming that we have a small set of core states, m of them. Let's say m is some small number, And the features of those core states, that convex hull covers all of the other state features, right? So this picture here, you can think of each star here as being a feature vector, right? So imagine that we have lots of states. Each of these stars is one state. And each of the states has a feature vector of 2 dimensions. And I've drawn all of those states sort of using their feature vectors. And I've chosen these blue stars to be my core states. And the requirement is that all of the orange stars, which represent all other states, lie within the convex hull of this, right? So, so obviously, you can see that in principle, it's possible to have a small number of core states, and then the number of states, as long as they lie in this region, can be arbitrarily big, right? So, and our algorithm will not be affected by that. And it is, in fact, it will still give close to optimal solutions with respect to all of the states, but without any computation that depends on the number of orange stars, right? And you can think of this as a generalization of state aggregation. So generally, one common technique that people use when you have lots and lots of states is that you aggregate states together. You take a group of states and you give them all the same feature vector, right? And then you can somehow treat all of these states as being one state, and you can do everything with them. The problem with doing that naively is that you don't get any bounds. Like you don't know how bad the solution quality can be once you have done the state aggregation. So this is a slightly more general assumption. So we are saying that we don't have to give all of these states the same feature vector as one of the core states. It just needs to be sort of in the convex hull of those blue states. Okay, so it's a relaxation of state aggregation. Okay, and you might ask what role this is playing. Like why do we need this condition? And the basic idea of this is that since you cannot possibly look at every single state, you have to generalize the values of all the states that you haven't seen based on the states that you have seen, right? So we are going to try to find the values of the core states and then generalize those values to the other states. Now, here, if you look at this left graph for a moment, so here I've drawn 6 states, and the x-axis represents, like, let's say, a feature representation, right? So let's say I have a one-dimensional feature representation. And I know that all of these states, like if I drew a line like that, then that's a fairly good approximation to the value of all the states, right? So I know that such an approximation exists. But if I happen to pick these 2 middle states, the 2 red ones here, and then use them to make a linear approximation of the values, so that results in this red dotted line going here, then that can be a really bad approximation to all of the other yellow states over here, right? However, if I pick my core states to be sort of the extreme states, the ones with the smallest feature representation and the largest feature representation, and then if I use those to select a value function that is accurate for those, then it's going to be fairly accurate for all of these states in the middle as well, right? So this is just like some intuition coming from sort of linear regression, that if you have to drop all of the points on which you're doing linear regression, you should keep the ones that are sort of the most extreme. And then you're going to get fairly good answers for all the ones in the middle, assuming that some good answer exists, right? And this intuition is coming from linear regression. The algorithm that we're going to describe doesn't use linear regression. It solves a linear program, but the intuition is exactly the same. So you can think of the convex hull idea as just being that I want to choose core states that are extreme in every direction, right? So instead of this one-dimensional thing, I do it in d dimensions. Okay, so moving on. And then I already talked about the saying that we have access to a simulator. Let me be more precise about what the simulator does. So let's say that our algorithm has access to a simulator that for the current planning state or any core state can randomly give you a sample of the immediate reward. So if you take the current core state or any other core states and take any action, then the simulator should be able to give you a sample of the immediate reward and the features of the next state. Right, so the simulator doesn't actually need to give you the next state because, again, the state space might be so large that you can't even represent individual states. Right, so it's just a one-step simulator, completely in feature space, right, and gives you the features of the next state. Okay, yeah. Okay, so that's so I won't describe the details of the algorithm, but I'll talk about sort of roughly what it's doing. So there was this paper from 2018. With Chandru, who was a postdoc here, and Shalabh Bhatnagar and Shaba. And this paper is talking about how, so you may or may not be familiar that you can write the value problem, the problem of finding the optimal value of an MDP, as a linear program. And the only thing that matters is that normally that linear program has way too many variables and way too many constraints, right? So the number of variables is something like the number of states, the number of constraints is the number of states and actions, right? But it turns out that if you carefully relax that linear program and drop some of the variables and drop some of the constraints, then you can prove that the value of that linear program is still fairly close to the actual value of the MDP, right? So our contribution is to take that idea and extend it and actually make an algorithm from it that can produce actions, right? So it's not just about finding values, because we already said that finding values is not quite enough to be able to find optimal actions. So our contribution is to extend this and say that based on this idea, we can actually write a fairly simple algorithm that does simulations on core states and the current planning state, a small number of simulations, and produces an action that's close to optimal. And the way that we do this, this might look scary that we are solving a linear program because we are used to these sort of online incremental algorithms that use some sort of gradient descent and minimize some error function, right? And it might seem scary because if you have seen the history of linear programs, they tend to be these large, complicated algorithms that kind of need a global overview of the problem. But there has been a lot of advancement in the field of optimization in the last few years. And one of the results is that if you take any linear program, you can write that as a min-max problem. You can write that as a minimization of something and a maximization of something. And so it becomes a saddle point problem. And then you can solve the saddle point problems using gradient-based methods. And so those algorithms end up looking very, very similar to the standard gradient-based, simulation-based algorithms that we are used to. The only difference is that instead of the objective function being a convex function, it's like a convex-concave function. It's a function of two variables. It's concave in one and convex in the other. And in our case, in fact, it's linear in one, linear in the other. So we can talk more about this so I'm not giving the details of the algorithm. I'll put up a slide with the algorithm after my talk is done. But I just wanted to reassure you that the resulting algorithm looks very, very similar to a gradient algorithm. And in fact, one of the gradients actually ends up being the temporal difference error, right? So you might have heard a lot that the temporal difference error is not the gradient of anything. But it turns out that if you have this formulation of the linear program, the temporal difference error does actually end up being a gradient. And in fact, then you can think of the resulting program as being an actor-critic method, where you're learning a policy and a value function at the same time based on gradients. Okay, so and the gradients come from the simulator. So we don't actually have exact gradients, but we have we use a simulator to sample gradients. Okay, and then this is our main result. So one thing I wanted to emphasize is that the algorithm that comes out of this is anytime, right? So it's an iterative algorithm. You can run it for any number of iterations that you want. And let's say that you have enough time to run it for t iterations, right? So if you run this algorithm for t iterations for a particular state S, then that uses the simulator m times a times t times, right? So m is the number of core states, a is the number of actions, and t is how many other iterations you use it for. And then it outputs a single random action. And that action is quite close to the optimal action. So if you take the expectation of v star minus q star under that action, then that is bounded by this quantity here. And this quantity has two terms. The first term, depends on the quality of our function of our feature representation, right? So epsilon, remember, was the quality of the feature representation. So this first term is telling you how good is this information that was given to the algorithm in terms of the quality of the feature representation. And then the second term is telling you how does the computation help, right? So as t increases, the second term will get smaller and smaller, and it will go closer and closer to 0. But even if you don't give it infinite computation time, if you only give it t computation time, then the performance bound is going to decrease like 1 over square root of t. So if you've been following the discussion that's been going on in the RLAI channel, so this is kind of the new scaling that Rich was talking about. The second term tells you how the quality improves as the computation time increases, and the first term tells you sort of what is the ultimate achievable quality in the limit of infinite computation time, and that depends on this epsilon parameter. And if you do this one state at a time, so that gives you a planning algorithm. If you take the policy that represents, right? So you just take that abstract policy that we have constructed here, and if you look at the difference between the value of that policy and the value of the optimal policy, then again you get a very similar thing. In fact, it's the same thing with just an extra 1 over 1 minus gamma factor, right? So these two terms are saying the second term is telling you how much computation you are using in the planning process for every state, and the first term is telling you the quality of your feature representation. Okay, so I hope that makes sense. So the conclusions are basically that, so we have shown that there is a simple algorithm which basically corresponds to planning on a small number of core states and actions for those core states. And as long as a simple geometric condition holds on the feature representation, which is that, let's say you construct a feature representation so that every single state is contained within the convex hull of the features of those states, then this algorithm is going to have a small value loss compared to sort of the optimal policy, right? Regardless of whether the optimal policy can be represented or not, or whatever form that optimal policy takes, regardless of any of that, we are going to have a fairly small loss compared to that policy. And sort of the second takeaway from this, sort of the general principle here, is that we do not try to explicitly find an optimal policy. So if you look at the algorithm that that I described later, we are not actually finding an optimal policy. We are using computation. So for every single state, we're doing a small amount of computation and selecting an optimal policy. And this kind of lines up with what Rich was saying in his talk about tracking, right? So sometimes maybe your goal should be able to find an optimal action for whichever situation you are in right now, rather than trying to find a global optimal policy that describes what actions to take everywhere. Maybe that goal is unrealistic, but if we have some computation available to us, then maybe we can. So I'll stop here. I'll put up this screen, which has this algorithm. It looks a little bit complicated, but it's not really. If there's any questions about what's going on here, I'd be happy to answer them. I do want to emphasize that there are these parameters, T, B, and eta, but they are not free parameters. In our algorithm, we tell you exactly what parameter values to use. So this is a well-specified algorithm, no unknown parameters of any kind. And it's a gradient-based algorithm. It's not gradient descent, it's gradient ascent descent for the value functions and sort of policy. And these gradient estimators can be derived from the simulator. So yeah, I'll stop here and I'm happy to take questions. Thanks.
Thanks, Roshan. There were a couple of questions in the chat, mostly regarding how the core states are chosen. So,
right.
Yeah.
So the core state. So in this problem, we are assuming that somebody has given us some set of core states, right? So you can think of it that way. We are assuming that somebody has given us some set of core states and a feature representation that satisfies this property, that every single feature vector lies within the convex hull of those core states. You can think about the exploration problem. So we are not handling the exploration problem in this setting. So you can think about exploration problem as finding the core states that have extreme feature values. Otherwise, if you're doing representation learning, right? So let's say that you have a deep network or something and you're learning these representations, then you can think of the core states as being maybe the states that you have visited in your replay buffer or something, right? And you are trying to come up with a feature representation that satisfies this property, right? So the core states are given to the algorithm. That's the answer. Sina asks, what about outliers? I assume that means, what if there are some states that just happen to not lie in the convex hull, like a few individual states that are outside. This result can probably be strengthened to say that if that happens a little bit, that's fine. So in fact, that is going to be one of our next things to work on, which is if you have an approximate way of generating these core states, for example, then you might also end up with features that lie outside the core states. And as long as those features do not contribute very much, you should be able to make some assumptions and say that the impact of that is small. But for this work, we are not dealing with that. Okay. Right, there's this question, is the idea of core state somehow related to the Kiefer-Wolfowitz theorem in this problem setting? Vaguely, yes. In spirit, it is similar. So for those who don't know, the Kiefer-Wolfowitz theorem says that if you have a bunch of vectors, for example, feature vectors, in a d-dimensional space, then you should be able to select a small set of those vectors that basically cover sort of the sphere containing those vectors covers all of the other features, right? So the thing with the Kiefer-Wolfowitz theorem is that the number of states should only depend on the number of dimensions. Here it can be bigger, right? So because of the nature of the MDP and the requirements on value functions, it's not enough to just select something like D or D squared features. you should, you need more than them, right? So in the worst case, it is possible that the number of core states is as big as the number of states. And if that is the case, then our algorithm doesn't give you any advantage. But if you're designing a feature representation, you should avoid that. So you can think of this as a design goal: make a representation where everything is within the convex of features. So what's the number? What's M? And it is the number of states, as Abhishek said. Sorry, the number of core states. Right. So the bilinear pi-learning algorithm. So the difference between sort of a lot of this saddle point-based algorithms and our algorithms is that all of them assume that they're kind of doing simultaneous value function computation and policy computation, and all of them have to assume one of two things. They have to assume that the value function of every policy can be represented in the feature representation. And if you kind of think about it, that's a very, very strong assumption. So it's not just V star that needs to be representable. They require basically every single value function and every policy to be representable. The other possible assumption that they have is that they assume that there is a small class of policies, and that the optimal policy lies close to that class, and all of the policies are kind of similar to each other. That their stationary distributions are close to each other. Chaba and I feel that both of those assumptions are really strong and probably can't be guaranteed in practice. So the whole point of this work is to avoid making any assumptions about what an optimal policy looks like, and also to avoid assuming that you can represent the value function of any policy except the optimal one. Because feature representations, it seems reasonable that a good action has a representable value, but it seems kind of unreasonable to say that no matter what policy you use, the resulting value function is representable. That just seems like unlikely to hold in practice. So any other questions? There's a new question by Matthew McLeod. What kind of feature representation would not fit this algorithm well? It seems like it would cover most realistic feature representations. I guess many binary features would create too many core states. Right, so binary features is sort of an interesting case. So let's say that you have a small number of binary features. You can think of them as lying on the corners of a hypercube. And then you know that the convex hull is going to be 2 to the number of binary features, right? But in practice, you often will use something like tile coding and so on. So you might actually end up with a feature space whose dimensionality is large, right? So binary features are an example of a hard case, but also an example of a case where you might want to use something like this. Because if you have a small number of binary features, then sort of the corners of the simplex are going to be 2 to the number of binary features rather than something else that comes from tile coding, etc. Are there any other questions?
Yeah, there's a comment by Rich in the chat.
There you go. Yeah. Right. Let me think about how to. Right. So it is a strong assumption. So it is a strong assumption that the values are close in every state. But remember, first of all, that is not an assumption, right? So what we are saying is that our algorithm scales with the quality, so it scales with epsilon, right? So the worse it is, the worse your algorithm is, but that's a smooth sliding scale. So that's one answer to that question. The other answer to that question is that indeed there might be some states that you don't care about too much, right? So separately from this whole core state idea, there might be some states where you really don't care about having a good approximation. So you're okay with the value function being far from the optimal value in those states. And in fact, all of these results can be transported to like a weighted setting, right? So instead of just requiring epsilon to be the max over all states of V star minus the best representable thing, you can have a weight parameter in there, right? And so if your weight parameter is really slow, then you're allowed to have a large deviation between those value functions. And then it turns out that all of these results work there as well. It's just the definition of epsilon changes to be this weighted maximum norm. But you have to make an additional assumption, and it's often called like the Lyapunov stability condition. And that assumption is basically saying that your MDP doesn't go from an important state to an unimportant state with high probability, right? So it's roughly it's saying that your MDP can't just jump from an important state to a low important state. Because if it could do that, then it's not correct to think of those states as being low importance, right? So yes, so depending on what we're looking for, it is possible to weaken the assumption. We haven't done that here for simplicity, but all of the work that Chandrasekhar, Lakshmirana, and Lakshminarayan's work does make that assumption. So it's possible to weaken that. Right, so do you need to, Ivan has this question, do you need to store all states, features, vectors in order to obtain the set of core states? So like I said, we do not, we assume that a set of core states is given to us. So we assume that there is some sort of either a design process or some sort of exploration phase that's giving us those core features, core states. But once those core states are given to us, we do not need to look at any of the other states features. So that's like a key idea of this work. It is cleanly separating the conditions that are needed on the core states. And we are saying that once you give us these core states, we can do everything else in planning without looking at any of the other states. And the only way to do that in general is to make some sort of global assumption like we are making with the core states.
Yeah, so we are almost out of time, so maybe time for one last question before we close.
And I'm happy to stay here if anyone has more questions. Also, if somebody peers at this algorithm and doesn't quite understand what's going on, I'm happy to explain it, but I'm here.
Yeah, maybe just a follow-up to Lee's question. So I guess maybe what he was also trying to get at is, do you have some idea of how this would be done in the online setting given a problem? Like, so suppose you weren't given these core features, but you were to discover them by yourself. So how would you kind of go about doing that? You have some
Right.
idea?
So I have some vague ideas about that. That is sort of the next, like one of the possible future things that comes from this work is how do you extend this to the online reinforcement learning setting, so rather than the planning setting. And yeah, I have some vague ideas. There are two possibilities, like I said. So one is that you can treat the feature representation as just given to you. And you can try to have some sort of exploration procedure to find these core states. And then you also need to say that you don't have a simulator anymore, right? So instead of having this one-step simulator, you have to make do with the samples that you're getting from the world, right? So that is in the realm of exploration, right? And so there's a lot of research to be done there about how you can do good exploration. The other idea is that instead of thinking of the feature representation as fixed and the core state as being given, what if you think of the core states as being given to you, right? What if you do like some sort of pass on your algorithm, you just follow some baseline policy, and you hit some states, and you think of them as your core states, right? So maybe the states in your replay buffer. Then the interesting question is, can you construct a feature representation that satisfies those conditions with those given core states, right? And I think maybe that is a more fruitful avenue to follow. How do you do feature representation while maintaining this core state idea? But like in a lot of game playing algorithms, right? So in sort of poker and in Atari games and so on, this planning algorithm can kind of be used directly, right? You have a state representation. It's really, really big, right? So it might be the memory contents, right? The memory contents of your Atari or whatever, and you can simulate from there. The only thing is that your feature representation might be really complicated. Okay, so Rich asks, why compare to optimality? Why not compare to the best you can do with the feature representation? So this work is kind of answering that question, because it's not really clear what it means. What is the best you can do with your feature representation, right? So first, you need two theorems really. One is the best you can do with a feature representation is this, right? And the second, what's an actual algorithm that gives you worse performance than that? And so we are kind of answering both of these questions here. If I go back to our result here, this first term is kind of saying what is the best you can do with your feature representation given infinite computation time. And then the second term is saying, okay, I can't quite reach that because I only have a finite amount of computation time, that's this capital T here. And so I'm going to be slightly worse than that. So you can kind of think of this result as answering both of those questions. What's the best you can do? And then what's the best you can do with finite computation? Okay, and Ahmed asks, how do you use core states in the algorithm? Let me go back to the algorithm. So if you think about kind of like the state of the algorithm, there's this variable theta here, which represents sort of an approximate value function-ish thing. And we are not going to say that this value function is actually a good value function or anything. It's a very special purpose value function that is only useful to estimate the value of one state. But then the other thing is these variables called lambda, and they represent sort of a distribution over core states and actions in the current planning state. Right, so you can kind of think of it as a stationary distribution over state action pairs, but it's not really. In fact, you can't find that. But so that's sort of the role of the core states in the algorithm, is basically to think of the core states and the current planning state as the only states that exist, and then plan on those states using the one-step simulator for those states. So it's kind of saying that instead of doing rollouts, normally you can kind of think of planning as, in principle, kind of doing rollouts. I'm looking at my current state and I'm like rolling a model forward. But the problem with doing that is that any error sort of blows up exponentially as you roll forward, right? And what this approach is saying, that I don't need to do those rollouts in time. I can just do planning directly with the core states without actually thinking about the dynamics over time. The core states just kind of serve that purpose. The important thing is, I said that this problem is almost like you were doing planning with just the core states, and that's not quite true. It has to be planning with the core states, but also using the the feature representation. Because if you do exact planning with the core states, then your plans can have no basis in reality, right? Because the value functions will correspond to all sorts of weird value functions. But the idea is that if you restrict your planning to value functions that are representable using your features, and you're using your features to generalize. So that's what I would say. The core states are being used as if they were the only states, but at the same time using the feature representation to generalize amongst the core states and other states as well. I hope that made sense. Yeah. Yeah. So this really is a synergy of the feature representation and the planning process. You cannot break this into two parts. You cannot think of this as something to do with the feature representation and then exact planning on some small set of states. It is really necessary to sort of tie together both of these processes and make sure that they work together, so that in the end you get something that is still meaningful, because neither of these things on their own is meaningful. I promised that some of the gradients of this, you'll have to look at the paper to find a full description. I'll post a preliminary version of the papers on Slack. It's submitted to NeurIPS, but yeah. So basically you end up with a saddle point objective function, which is this f function here. It's a function of theta and lambda. So theta is sort of a value function, lambda is sort of a stationary distribution, and the gradient of f with respect to lambda happens to look exactly like the TD error, right? It's the sample reward plus the gamma discounted change in the feature vector when you're going from S to S prime, where S is sampled according to the stationary distribution lambda, and S prime is sampled according to the MDP. So the policy gradient part of this algorithm is exactly using TD errors. The value estimation part of this algorithm has this gradient here, the second line here. And that's not quite a TD error. It's not based on the reward, but basically it's trying to make sure that the value function is stationary according to this policy. And more details in the paper.
So Roshan can stay back for some more time if people have more questions, but let's all thank the speaker for their talk. Thanks, Roshan.
Thank you, everyone.